what is a quantum cascade laser? Now, basically, let me put this over here. A quantum cascade laser is a device that can generate a beam of light using layers of semiconductors. Now, it's a bit more complicated than that, but we're going to get into it later. However, that's basically what the device does. It generates a beam of light with multiple layers of semiconductor material. Now, the beam that it generates, it's generated by electrons that are transitioning from one energy state to another. That generates multiple photons from a process that's called stimulated emission. It's right here. And that radiation that has been stimulated emission can then be amplified by having the photons move back and forth between two mirrors. So you have the main laser, you have two mirrors, the photons are going to go back and forth, and if they have the same wavelength and the same frequency, they're basically going to quote-unquote merge, and they're going to increase their intensity. And if you do this multiple times, the process repeating back and forth, you're going to have a beam of light that's going to be very, very dense in photons. And what we do is then one of the mirrors is going to have a little hole, and from that hole you're going to have the beam of light, which we call a laser. And basically, that's what a laser is. That's the acronym. It blew my mind the first time I read it. I love when the names actually explain the phenomenon. So yeah, this is very, very key for different methods of spectroscopy that we will talk later. However, for this specific part, I simply want you to know that a quantum cascade laser generates a laser with semiconductor materials, and that a laser is created by this process. Okay, so now if we compare different lasers, in this case a quantum cascade laser with a semiconductor laser, although both uses semiconductors, they're very different. We have four different things that I'm going to focus on the comparisons. Basically the active region, the part where it basically creates the laser, the wavelength range, which is the range that you're going to have thanks to the laser for the photons, the principle that it uses, and how efficient the laser is. And the main difference between both is that a semiconductor laser, a normal one, is made out with one single active layer of a semiconductor. It's going to have two different parts, the positive part and the negative, and through that specific flow, you're going to have your phenomenon. While on the active region of the quantum cascade lasers, you have multiple layers of semiconductors. We're going to show how this works later. However, the phenomenon that the quantum cascade laser uses is called inter-subband transitions, and it's done from the electrons moving from one quantum well to the other. And all that's going to make sense later, no worries. Now, for this specific part, I simply want you to see that both are semiconductors, but they're very different, including their wavelength range. A semiconductor laser will generate photons that have the energy and the frequency in the near infrared region and in the visible region. While for the quantum cascade lasers, you're going to have light that's emitted at longer wavelengths, such as mid-infrared and far infrared. And depending on what you want to use, one's better than the other, right? They're not objectively better, depends on the application. But we're going to focus on the quantum cascade lasers in this case. So, I'm going to give you a brief history of the different topics that helped generate what the quantum cascade laser is. Now, the first thing is in the late 1800s when the concept of conductivity was discovered. Basically, is the property that allows materials to conduct electricity. Something that has high conductivity is known as a conductor. Something that has very, very low conductivity is known as an insulator. And basically, those are the two things that were discovered back then in the late 1800s. After that, in the 1900s, in the early, you had the concept of solid-state physics starting to bloom. Now, basically, when we talk about quantum mechanics, we explore systems that are very, very, very small. Normally, when you do a Schrodinger equation and all that, you work with one electron, maybe two. You don't work with an actual solid material, right? And due to that limitation, solid-state physics started to emerge. And this helped understand more closely what was causing the electrical conductivity in materials. Now, from that point on, in the 1920s, they discovered that when an electron moves from one place to the other, the absence of that electron leaves a hole, quote-unquote hole, that has a positively charged charge. And in this case, it's going to be partially due to the absence of the electron. And this seemingly small thing is critical for the development of the semiconductors, which then in the 1930s and 40s were discovered. The semiconductors are basically materials that are the middle child between conductors and insulators. In this case, we simply started seeing what were the different types of semiconductors, what they did, and the fact that they have both best of both worlds, but on different levels. Now, when in the 1950s to 1960s, scientists discovered that although semiconductors are between a conductor and an insulator in terms of conductivity, you could actually manipulate that electrical conductivity of a semiconductor by adding specific impurities to the material. So by adding an element that was not part of the semiconductor, you can actually make it do something else, or at least modify its conductivity. And this process is called doping. After that, in the 1950s to 60s, the first PN junctions were created, which are basically an interface where you have a positive and a negative semiconductor, and through that difference, you can allow electricity to pass. And due to this specific PN juncture, it allowed for different electronic devices to emerge. For example, the transistors and the diodes, which are very important for our area of expertise. Now, after the PN junctions, then we started to get to the actual meat and potatoes of the argument between what is a quantum cascade laser. And the first thing is the molecular beam epitaxy process, which is a technique that allows you to precisely control the thin layers of materials, and that allows us to generate a material with a specific width, and we can actually make layers on top of each other, and layers on top of each other, minimizing the amount of air or other things that would be present if you simply sandwiched the things, right? We're literally creating the layers on top of each other. And this is going to be very important. After that, in the 1970s, the concept of the quantum well was being discovered. And we're going to talk a little bit more about this later when I explain what it is. However, for simple words, basically a quantum well is a semiconductor that is sandwiched between two other semiconductors. And due to the difference in the band gap, it creates the environment for the particles inside the semiconductor to behave similar to the model that we use in quantum mechanics known as particle in a box. I'm going to get into that a bit more later. However, this invention of the quantum well was crucial and very, very important for the development of quantum cascade lasers. Then in the 1970s to 1980s, it was discovered that when you do a quantum well, and you have a specific thickness, right? You go to a specific low thickness between the two layers, you can actually quantize a band. A band being in solid state physics you have these two bands with a material. You have the conduction band, and the valence band. And between that, you have the band gap. The bands, basically, when you have a solid has millions and millions of different electrons due to the different atoms that make up the solid. And those different electrons are going to have multiple energy levels. And since you have such a great amount of energy levels, you basically go back into seeing matter, or at least the energy in the bands, as continuous, right? It's not actually continuous, but it basically almost behaves like it's continuous. You have so many layers, one with each other, that it's basically the same as saying, okay, it's simply a band. It's a band, and you use it, you go from one to the other, and you're okay. Valence band is where all the outer electrons are in an atom, and the conduction band, you can actually give it enough energy to an electron, and it will move to the conduction band and do other things. What we're saying in here in the 1970s and 80s is that if you have a semiconductor that has a small enough width, you can actually quantize the levels inside of a conductor. Again, you can actually go back and quantize those layers. So instead of having that band, which looks almost continuous, you're going to have different energy levels. And this is going to matter when you see how we're going to use them. However, it's a very important discovery for quantum cascade lasers. And after this, if you put everything together, then you get the first quantum laser, the Quantum Cascade Laser, created by Federico Capazzo in the early 1990s. And basically, the effect that it uses is it transitions electrons through intersubbands, and that way it generates a beam of light. And we're going to see how it works right now, how a QCL works. So, basically, semiconductors. We have a solid. In the solid, we have multiple electrons. They're all moving freely from one side to the other. We saw that semiconductors is the middle child between the conductors and the insulators. And we saw that all of these different materials have one thing in common. They have bands. They have the conduction and the valence band, and they have the gap between those bands, which we call the band gap. And what differentiates one material from the other is the size of the band gap. For conductors, it's really small, and since it's really small, you need less energy for the electrons to go from the valence band to the conduction band and then have a flow of electricity. With the insulators, since they don't have a lot of electricity flow, that's what makes them insulators, the band gap is much, much bigger. And the semiconductor, since it's a middle child, is going to be bigger than the conductors, but smaller than the insulators. And this is very important because depending on the semiconductor that we use, we can vary the band gap. And that's what we do to generate a quantum well. We have a semiconductor that has a very, very small band gap, and we sandwich it with two other semiconductors that have a much, much, much larger band gap. Here we can see the difference. The conduction band up here in the top, then you have the band gap, and you have the valence gap, the valence band below. This is going to generate a condition for the particles inside, which are the electrons. It's going to create a condition where they're going to be confined. The band gaps of the two materials that are very, very large are going to act as the potential barriers that usually confine particles when talking about particle in a box, which is basically a model where in order to make complex calculations for the wave function, for probabilities, for energy levels, etc., what it does is it confines it confines an electron inside a specific amount of space to simplify the equations. And that's all well and good, but it doesn't really do much for us in the real world unless If you do a small enough semiconductor layer, and when I mean small, I'm talking like 1 to 10 nanometers. It's so small that if 1 nanometer, if you measure the diameter of an electron, in 1 nanometer, you can basically fit over 500 electrons if you touch them side by side like this. So that's very, very small. Okay, 1 nanometer is nothing to scoff at. And if you create a semiconductor with that specific width, with those two potential barriers from the other semiconductors, you're going to quantize the levels of energy inside of the conduction band. And this is very, very important, because if we have levels inside of a band, which we call subbands, we can then transition the electron from one band to the other. And if we do that, when it goes from one high energy state to the lower state, it's going to generate a photon, with the energy level being the difference between those two energy levels where it transitions. And the great thing about this is that we can use this to generate multiple photons. And how we can do this is that we generate, and we don't generate, we give electricity to the electron. The electron is going to go to an upper higher state of energy. And when it's in that specific high energy state, it's then going to go back below in a lower energy state, and it's going to liberate a photon. But it's not just going to do that. It's going to do quantum tunneling from one quantum well to another quantum well. And that's where the multiple layers of semiconductors go into play. So you have multiple semiconductors here. And let's say that this one right here that's with the dashed lines, this is going to be our quantum well with the two semiconductors by the side. And then you're going to have another quantum well. And you're going to have another quantum well. And what's going to happen is that due to the phenomenon of quantum tunneling, where there's going to be at least an amount of probability where the electron can pass through a barrier, you're going to generate the photon, the electron is going to move to the other part, and then it's going to, yet again, emit another photon, and then it's going to go back and do the quantum tunneling to the other quantum cascade to the other quantum well, And if you do this enough times, you're going to get the effect of the quantum cascade laser. But before that, very important that you identify the difference in between the transitions. When I'm talking about the quantum cascade laser, I'm talking about inter-subband transitions. So you have a band, the conduction band right here, and you have different layers. These layers are the subbands. And you're basically moving from one subband to the other. That is an inter-subband transitions because it's between subbands. If you're going from the conduction band to the valence band, that is an interband transition. You're going from one band, one whole band, to another whole band. And what is the difference between both? The difference is that depending on the amount of energy that you emit, you're going to have different photons of different wavelengths. If you do interband transitions, you're going to have photons that are in the ultraviolet and the visible region. While if you do inter-subband transitions, you can have photons that are in the infrared region. And this is incredible. This is very, very good, because then it allows us to have infrared light with this laser. And if we can use mid-infrared light, we can characterize samples, we can detect samples, classify them, quantify them, etc., by using what we know as spectroscopy. We're going to get there later. Now, if you use this concept all together, what we have is a quantum well where an electron is going to be excited by electricity, then it's going to go down, and when it goes down from one subband to the other, the inter-subband transition, it's going to generate a photon. And then that electron is going to use quantum tunneling to go to the other quantum well And by doing that, then it's going to lower its energy state again, because the quantum wells are going to be slightly below the previous one, right? The previous one is going to be at a specific height, the other one's going to be lower, and the other one's going to be lower, and the other one's going to be lower. And by doing that, when the electron does the quantum tunneling, it's going to keep lowering its energy state, and it's going to keep emitting photons. And all of those photons, they're emitted by multiple electrons, because this example is simply with one electron, but we're going to have multiple doing this. Then you have your cascade of electrons going from one place to another, generating all of the photons. Those photons are going to be dense, and then you can do the mirror thing going back and forth, and you have a laser. And that's a quantum cascade laser. Okay, that's how we generate a beam of light using multiple layers of a semiconductor. Now, that was a lot. When we compare normal lasers, right, the traditional lasers, with the quantum cascade lasers, the bigger difference is that a quantum cascade laser has a more specific phenomenon where it transitions from intersubbands from one to the other to generate the photons. However, there's also different things, right? When you have a traditional laser, you have a medium that's usually a crystal or a gas that you basically pump electricity to, and then it's going to generate the effect and produce a light beam. With a quantum cascade laser, you can use electricity to then make the different intersubband transitions from one quantum world to the other to generate the beam of light with layers of semiconductors. And that's the main difference between both. However, the other great difference is that traditional lasers are usually in the visible region and the near infrared region, while the quantum cascade lasers are in the mid-infrared and far infrared. This is such a great thing because you have more place to do studies. You have more different regions to do other things. And in this case, mid-infrared and far are used a lot for characterizing things. And that's why we need it for spectroscopy. And that's why quantum cascade lasers are so valuable for infrared spectroscopy. Spectroscopy being the study of how light interacts with matter. Very, very curious is the fact that if you basically collide a photon with a specific material, specific molecule, it's going to act in a specific way at specific frequencies. And that specificity is what allows me and allows us to be able to characterize different molecules. And that's what makes spectroscopy such a valuable area of study and why it has so many applications. Now, a normal spectrometer, what it basically boils down to is this specific diagram where you have a light source. It's usually a lamp when we're talking with infrared. However, with quantum cascade lasers, we can have a laser there, right? That would be a light source. The light source then goes through a collimator to make parallel lines of the beam. Then it goes to a monochromator where it then selects a specific wavelength that specific wavelength goes to the sample and is going to interact with the sample in a specific way. Let's say that we have a graph right here and we did all the process. We generated the light, went through the monochromator, then you have a specific light that's going to hit the sample, let's say at 200 nanometers. And when it hits the sample, it might do nothing. It might just look like this. And then if you go at a different wavelength, it might still look like nothing. It might still look like nothing. But then at some specific range, it's going to increase in value. And then it might still be nothing for the other frequencies, but then it might increase again, and then again. And it even might be wide. And that's what makes this technique, this specific device, so valuable, because it gives us specific information for specific samples. Now, what is the thing that I'm actually measuring that's being fluctuating, right? The thing that I'm measuring is absorbance or transmittance. Basically, if you have a sample, in this case, the thing that I'm using right here is a transmission optical setup. Basically, you have the light, it's hitting the sample, and then it's going past the sample, going to the detector. This is called a transmission optical setup. And in this case, the sample is going to absorb some of the frequency from the light. If it actually creates it's not a reaction, a specific transition in the sample, going from one energy level to another. For this to happen, you need a specific amount of energy. And this is why at some specific points, nothing happens. When you have the specific amount of energy necessary, the sample is going to produce an action, either a vibration, a rotation, etc., etc. And then the sample is going to let through all the other energy that it didn't absorb. And that's the energy that the detector then gets. So you have the initial intensity, which I'm going to call I0, and you have the intensity after the sample had absorbed. And with those specific values, I can calculate what's known as transmittance. And then by an equation, I can then change it to absorbance to only see when the sample is absorbing. So this is basically a crash course to what a spectrometer does. And it's very, very useful. I've said it a lot. The applications are immense. This is specifically one of the advantages of using QCL in spectroscopy. One of the greatest things is that it has flexibility with the wavelength of the laser. Normal lasers that are used for Raman spectroscopy, for example, are monochromatic. They have only one specific wavelength, and they vary a little between that specific wavelength, but they try to stick into that specific wavelength. But if you use QCLs, quantum cascade lasers, you can actually vary the wavelength of your laser, which makes it actually usable for infrared. The other thing is it has a high output power. If you have high output power, the higher the power, the lower the concentration can be. You can detect samples, you can detect the signal of a sample that has very, very, very little concentrations if you have a powerful enough laser. The other thing is that since it has such power, it can actually penetrate different different materials. Can penetrate crystals, can penetrate possibly even paper, different things where materials can be concealed. Now, in addition to that, it has high resolution. Normally, resolution is the amount of points you have in order to create a band or a vibrational mode. So if I use this amount, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I use 12 points to create this specific band. But if I have a higher resolution, I'm going to have more points for that specific band. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 8. And there goes. I cannot count that. All of those in English that fast. But yeah, you have more points for that specific band. And that's going to allow you to see even more vibrations that you probably would have missed with a laser that has less, a spectrometer that has less resolution. Let's say that you have this specific band, but if you have a high enough resolution, instead of seeing this, you might have seen this. And in reality, this would be the correct band for the spectra of that sample. However, since your resolution was so small, it simply detected the points that generated the big curve, because the spectrometer just gives you points. It just gives you a specific amount of transmittance or absorbance for a specific wavelength. And after you have those specific points, it just generates a smooth line between them. So if it's not as specific as possible, you might miss other peaks that basically were the entire peak that you saw previously. So the Quantum Cascade Laser has high resolution and can accomplish this. The other thing is that it has a compact size. And as you can see here, this is a Quantum Cascade Laser that is the size of a coin, basically, of a quarter. However, this is from Block Engineering, which is one of the companies that we usually work with when we're working with QCL spectrometers. And specifically, this is that amount of small, but it's just the laser. You still need the components of the spectrometer, so it's going to be big. However, since we can create such small lasers, it allows us to create instruments that are very, very small. They're more compact and can even be portable. Here you have one of the instruments that we have in our laboratory called the Laser Tuned QCL Spectrometer. We use it to detect chemicals and biological threats, and it's being used currently. We have over like 3 or 4 of these laser tunes. They're really good. They have a lot of sensitivity. It has allowed us to get really, really big peaks and get to lower and lower limits of detection. It's a very, very great instrument. Now, what are the different applications that QCL has been used in spectroscopy? It has been used for environmental monitoring, where you can monitor gases, particulates, pollution, etc. Chemical analysis is basically the bread and butter. You're going to see a lot of studies where they have used QCLs to detect explosives, to detect different chemical and biological threats. Medical diagnostics, it has been used to detect disease markers in biological samples, in urine, in blood, and other places. You also have industrial process control. You have a specific lot that you want to verify if it's basically uniform, if the concentration of the active pharmaceutical ingredient, for example, is constant in all of the different areas of the lot. You can do this with QCL. Security and defense, I've talked previously about detecting explosives or biological threats that are basically great for preventing incidents and other catastrophes. And even in astronomy, QCL has even been used in astronomy. So here are the 3 different optical setups that we use in the lab. The most common one is transmission, in which you simply have the beam go through the laser, then go through the detector. This is going to give us a sample that we can compare with other infrared samples, like the different library samples of the spectrum. And then we have attenuated total reflectance, which simply has the laser pass through this material. Then it's going to be creating a set of oscillations in a specific material, basically like a diamond. I think it's zinc selenide or something like that. Depends on the material. And all of the different fluctuations are going to create evanescent waves. And those waves are going to hit the sample in different parts. So it allows you to have a measurement that's going to be more representative of the sample that you took. It's not going to be just a dot, just a point. And then that goes to the detector. And then we have the grazing angle, which is basically a new patent that we're trying to develop. Our students, Jorge Plata, our professors, Samuel Hernandez, Ricardo Infante, and Leonardo Pacheco, they are currently working on the patent. I'm not sure if they already published it, but I know they're working hard on patenting this specific arrangement, and that's why I cannot show it yet. But we have these 3 different types of optical setups that we use, and they're very, very useful for different applications. Depends on what you want to do. Now, more workshops are going to be in the way for learning how to use them. Here is me showing the students how to use the laser tuned QCL spectrometer, specifically in transmission mode. And I'm going to be working on creating more workshops for different people, either more undergraduate students that work with us, people outside of our group. We want to keep creating workshops so that we can give something to the people. We want to educate them on how we can use spectroscopy, specifically QCLs in this case, to detect different threats. Why is it such an important thing to learn what spectroscopy is and all of those stuff. So here are my references, and thank you for your attention. If you have any questions, feel free to ask.